Press the bell icon on the YouTube app and never miss another update.
Good morning, friends. So today we have the next discussion of chemical bonding to continue with, and the discussion we are taking this time is the concept of formal charge. Certain things that you need to understand about formal charge are that the concept of formal charge is relative. So this formal charge concept does not take care of the electronegativities of different atoms. It's a relative charge in which we want to find out what is the apparent charge and what is the charge that can be present on a particular atom in a given molecule. Although the charge may be present on some other atom, but we consider a central atom to be the region where this charge is apparently present. So what exactly is formal charge in any molecule of an atom equal to, and how can we calculate formal charge of different atoms in molecules respectively? So if you want to find out formal charge, what exactly is it? Formal charge of any atom equals to what is the number of valence electrons in that particular atom, and what is the number of shared electrons by that atom out of the valence electrons, and what is the number of unshared electrons, which in simple language is also called as lone pair of electrons. So these are your bonded electrons, valence electrons total, out of which how many have bonded. So these are, we can call these as bonded electrons also, how many have participated in bonding. And then you have got unpaired electrons, or sorry, you have got unshared electrons, electrons which have not been used. So that's technically lone pair of electrons. So you can call these as non-bonded electrons also till the time bonded electrons are there. But when we talk about atoms shared, atoms are shared between two atoms. At a time, central atom, suppose I have the molecule of AB3, correct or not? So A will be sharing electrons with B here, and B here. At a particular time, we need to consider only one bond to calculate the formal charge on that particular atom respectively. So the number of shared electrons here is 2 only. Also the total number of shared electrons by A on the whole with all the 3 atoms is 6. Did you get the concept clear or not? So the shared electrons, they are between how many atoms? 2 atoms. So we'll say S by 2. So formal charge on an atom equals to the number of valence electrons minus shared by 2. How many electrons are shared by 2? Because it's between 2 atoms, minus unshared, which are lone pair of electrons. So these are your valence electrons, these are shared electrons, and this is lone pair of electrons respectively. We will move in the atoms like we got carbon, we have nitrogen, we have oxygen, and we have fluorine. So when you move from left to right, electronegativity is increasing, correct or not? So if these atoms are making bonds with some metal atom or with some atom, with some central atom, we will have to see what is the formal charge on the central atom. We can use this formula to calculate it out. Let us take one simple example to understand the concept of formal charge calculations. See children, if I have an ion like CO3 2-, so rather than taking ionic molecule into consideration, let me take a simple example into consideration like water molecule. Clear or not? We want to find out what is the formal charge of oxygen in water molecule. Apparently, if you see, is there any charge which you can see on the atom respectively here? No. So I would say generally formal charge equals to 0 for oxygen here. Let us see whether it is correct or not. Now, formal charge of oxygen will be equal to, what is the number of valence electrons for oxygen? 6, correct or not? Minus, how many electrons are shared out of those 6 electrons? Obviously 2, because when you look on the structures of water molecule, we have this structure, correct or not? So 2 electrons are shared, so 1, 2. Total, how many electrons are still remaining? 4. So what are these 2? Lone pair of electrons. So they are unshared electrons, correct? So 6 minus shared, how many? 1, 2, 3, 4. Oxygen is sharing how many electrons? Faster. 4. So 4 by 2 minus how many are unshared electrons? 4. So that makes it 2 will be 4. 6 minus 6 will be 0. So what's the formal charge on oxygen here? 0. Correct or not? Clear. Now if you convert this water into H3O, I'm not showing any charge here at all. I will find out what is the charge on oxygen. Generally, if you write down, we will write it is H3O plus. Yes, because one of the lone pair of electron has been used for bond formation and it has been given to a proton and we are getting the hydrogen ion. Right or not? So we can see general structure wise there is a positive charge on it. Let us see whether this positive charge is existing there or not. Let us draw the structure of this. Oxygen, you got hydrogen, and you got hydrogen. So, and you have got one lone pair of electron present. Correct or not? Last time we have done hydrogen ion with one lone pair of electron. Hybridization will be sp3. It will be triangular pyramidal in shape. So H3O molecule with no, initially I was not knowing what's the charge on this atom respectively. Here also I am drawing it in the same way. We will see what is the charge, formal charge of the oxygen. Let us see that. So oxygen, what's the number of valence electrons, children, for oxygen? 6 minus. How many are shared? 1, 2, 3, 4, 5, 6. 6 by 2. Correct or? Minus. How many unshared electrons are there? 2. Clear or not? So that makes it 3. So 6 minus 5 will be equal to plus 1. That will be the charge on oxygen. Am I clear here? One more molecule if you look on. See, if you look on the molecule of BH3, right? Boron has how many valence electrons, children? 3 minus. How many are shared? Very simple to do it through Lewis structures. How many are there? Shared 6. 1, 2, 3, 4, 5, 6 divided by 2 minus unshared 0. That makes it 0. So formal charge is 0. Right. What's the molecular? BH3. If it is BF3 or if it is BF4, if you take into consideration BF4, we don't have any charge here on the molecule itself here. Right. Boron with 4 fluorines have made bonds with it. Right or not? Right or not? So we are not just, actually boron can make how many bonds? 3. If it has made 4 bonds, that means it has already gained 1 electron. So charge on boron should be minus 1. Yes or no? Let us see that whether it is possible or not. Boron, valence electrons, V minus shared by 2 minus unshared electrons. So what is formal charge on boron equal to? Valence electrons for boron 3 minus shared, how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 2 minus unshared 0. That makes it 4. So 3 minus 4 will be minus 1. That's the charge on the boron, minus 1. But look here. Why did I see the concept of electronegativity of atoms is considered? And it's a relative concept. If you look in BF4, children, which is technically a minus charged. If you look on BF4, children, you will find out electronegativity of fluorine is highest in periodic table, which is 4. And for boron, it's almost a 2. Now we know electronegativity difference between the two. That is electronegativity between boron and electronegativity between fluorine. How much for boron, children? 2. And for fluorine it is 4. So it's 4 minus 2, it will be 2. This is more than 1.7. So the characteristic of bond will be more ionic. So this negative charge should be more towards what? Fluorine. But we are calculating that negative charge should be present on what? Boron. So keep it in mind. The concept of formal charge is a relative concept. Many a times the charge will be apparent on the molecule, but don't guess it for full-fledged part. That charge, whatever we are calculating, belongs to that particular atom respectively. Am I clear with this thought here? One more example, children, we can take into consideration here is CH3. There are many ways of taking CH3 into consideration. So we will take here into consideration CH3. I'll say both the things here. I'll talk about CH4 also. I'll talk about NH4 also. So I'll take different molecules into consideration so that we can calculate their formal charges respectively. Right, children? Yes. Let us see that. Correct. Let us take CH3. Correct. What's the valence electrons for carbon? Faster. Valence electrons 4 minus how many are shared? 6 by 2. How many are unshared? 0. That makes it 3. So 4 minus 3 will be plus 1. What's the charge on carbon here? +1. It means this atom is a carbocation. And how can you get this? CH3Cl. You know SN1, SN2 mechanisms, you have read about alkyl halides already. So chlorine will take electrons away, the molecule will become Ci3 plus. You are getting carbocation or not? A primary carbocation. What's the charge here? +1. Is it clear or not? We can have a carbanion also coming to play due to heterolytic bond cleavage. So we can have CH3 with a negative charge on carbon. If that is the case, apparent charge you have here, what's it? Negative. Formal charge wise we will calculate it. Valence electrons 4 minus shared 6, yes or no, by 2 minus unshared. How many unshared electrons are there? 2, yes or no. So that makes it 3. It will be -1. You are getting the things clear here? Okay, what about this molecule? If I am drawing the molecule like NH2 minus, draw the Lewis structure. N, you got H, So actually I am not drawing Lewis structures, I am directly drawing bonds here. NHH. So nitrogen, how many valence electrons on the whole? 5. It has gained 1. Negative charge is there. Correct. Total 6. So how many it has made use of? 2. So how many are still lying there? 2. So how many lone pairs you got here? 2 lone pair of electrons. Correct. So shared valence electrons 5 minus shared 1, 2, 3, 4. 4 by 2 minus unshared 4. So that makes it 2. So 5 minus 6 will be -1. That's why NH2 minus. So what's the charge on nitrogen here? Minus. Are you getting the formal charge concepts here clear? One more cation we will take, NH4 plus. Yes or no, children? NH4, nitrogen, formal charge on nitrogen will be faster. Nitrogen, valence electrons, quick, 5, shared, 8 by 2 minus unshared, 0. You can have a look on that. Nitrogen, it had 1 lone pair donated to hydrogen. You got hydrogen, you got hydrogen, you got hydrogen. Because this is a coordinate bond, right? Donated via lone pair of electrons. So one is lone pair of electron has been donated to a proton. Obviously charge on nitrogen should be +1. And here it will be 0 because hydrogen has come not as hydrogen. It has come out as a proton. It has come towards ammonia as a proton. So it will be 5 minus 4. That will be +1. This is the charge that you got on nitrogen. How much? +1. This is formal charge. Let us make things typical now. Say children, I got a molecule of carbon CO3 2 minus. We all know it comes from H2CO3. Right? So when the breaking will occur, you will have carbon double bonded to oxygen. Then you got oxygen with a minus charge. So 1, 2, this is the minus charge. 3, 4, 5, 6. Because it has gained 1 electron from proton. Yes. Let us forget about here. We'll put 1 more. So it has bonded up with what? Hydrogen. Here also oxygen. 1, 2, 3, 4. Then 1, 5, 1, 6. And this is bonded with what? Hydrogen. Is it clear? Once it breaks, what does it give out? 2 protons. Once it has given 2 protons, this proton has been lost as what charge? Positive charge. So you can have this electron belonging to oxygen and this electron has been gained. So we are showing this one as a pair of electron inducing negative charge. Here also as a pair of electron inducing what charge? Minus charge. Am I clear with thought here? Let us calculate the formal charges on carbon, oxygen number 1, oxygen number 2 and oxygen number 3. First of all, let us do it for carbon. Right. How many valence? You can see that carbon has how many valence electrons? 4, 1, 2, 3, 4. Does it have any electron in the valence shell which has not participated in bonding, which will be a lone pair of electron? Obviously your answer will be no. So what is the number of valence electrons? 4 minus. What is the number of shared electrons? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2 minus. How many unshared electrons? 0. So that makes it 4. 4 minus 4 makes it 0. So what is the charge on carbon? 0. Now have a look. See, if you are logical enough, this oxygen's formal charge should be -1. This should be -1. What is this one? 0. Naturally, this oxygen should also be 0. Let us see that. You are getting the point. Now let us see this oxygen number 1. Oxygen number 1 on carbonate ion, right? So I'm drawing it out. I'm drawing only one bond. C double bond O, correct? So how many electrons have been used here by oxygen? 2. How many are still pending? 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is formal charge. Will be how much? Yes. Valence electrons 6 minus shared 1, 2, 3, 4. 4 divided by 2 minus how many unshared? 4. So that makes it 2, 2 will be 4. So minus 2 minus 4 will be minus 6. So formal charge on oxygen number 1 is how much? 0. That's what I mentioned earlier. Am I clear with the thought, children, here? Next, let us see about this oxygen atom. This one, right? What's the number of valence electrons? We know 6 minus. How many are shared? 2 by 2. How many are unshared? 1, 2, 3, 4, 5, 6. So 6. So that makes it 6 minus 1 minus 6. That makes it 6 minus 7. That makes it minus 1. So that's apparent charge. That's a formal charge you have got here. Minus 1. And obviously this one also will be minus 1. So we can say, children, that oxygen number carbon, formal charge of carbon in carbonate 0. Formal charge of oxygen number 1, how much? 0. Formal charge of oxygen number 2 equals to what? Minus 1. Formal charge of oxygen number 3 equals to minus 1 as well. Am I clear with this? We'll do one more example, few more examples so that we can get clear with the formal charges respectively. Let us do it for a complex ion like sulfate, SO4 2-. I think for every one of you it should be clear now how exactly we can go with the calculation of formal charges respectively. Right. Yes, sir. Let us see that. Okay. So which one I will take into consideration now? Sulfate ion, SO4 2-. We already know it is coming from where? H2SO4. So you can see that quite clearly here that 2 oxygens will have the formal charge of minus 1 and 2 oxygens formal charge will be 0. I am drawing general Lewis structures of sulfate ion. So sulfur, how many valence electrons it has? 1, 2, 3, 4, 5, 6. It has 6 valence electrons, correct? One side oxygen, other is also oxygen, other also oxygen, and other also oxygen. Because there are 6 electrons, first of all, let me do one thing. I will make one single bond with all the oxygens respectively, because this sulfur is a central atom for us, right? So I will make one bond with each, because each oxygen is attached to sulfur. Is it clear or not? There is no proxy linkage here in SO4 2-, right? So we have how many electrons left out on oxygen now, sulfur now? There are 2. And this oxygen, let's make a double bond here, and let's make one more double bond here. Done. So this is done. These 2 electrons have been used up. How many electrons are still free on this sulfur? So 1, 2, 3, 4, and 5, 6. Done. This oxygen is not stable still. These are stable. 1, 2, 3, 4, 5, 6. Now I'll show it here. 1, 2, 3, 4, 5, 6, 7, 8. What about this one? 1, 2, 3, 4, 5, 6, 7, 8. What about this oxygen? Sulfur. Hypervalent, right? So it has made one bond with what? Oxygen. Single bond has been made with oxygen or not? Then this oxygen will have 1, 2, 3, 4, 5, 6, and then there is 7, 8. There is a negative charge on this. You can see that. SO4 2-. Where from it is obtaining it? This negative charge is coming from proton. And again here, 1, 2, 3, 4. Clear or not? 5, 6. Negative charge. 7, 8. Clear or not? You might ask me, sir, how oxygen is having the 7 electron calculation here? Very simple, because it has gained 1 electron from where? Proton. Let me remove that proton off here and we'll be negative charge here. Correct, children? So everywhere we will calculate formal charges now. So it is natural. What's the charge here? Minus 1 here, minus 1 here, 0 here, 0. Yes? So according to calculation also it is coming, but in a molecule it won't be given like this. You need to find out a proper Lewis structure as well. And if the Lewis structure is also not given, by using this formula, what? Valence electrons, so formal charge equals to valence electrons minus shared by 2 minus unshared electrons. These are lone pair of electrons. This is valence electron, because from valence electron only shared by 2. So shared by 2 means half of the atoms will belong to that atom. Out of valence, shared will belong to that valence shell. Unshared will also belong to the valence shell. Now we need to see which of the two are more. So according to that, formal charges will alter, formal charges will change. Correct. Now let us see this sulfur's formal charge here, children. So formal charge of which one? Sulfur. What is it equal to? What's a valence electron? 6 minus. How many are shared? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 minus 2. How many are unshared? 0. That makes it 6. So formal charge of sulfur, how much, children? 0. So you got formal charge of sulfur here as 0. Clear? Let us see this oxygen. I'll mention these oxygens as oxygen number 1, number 2, number 3, number 4. You can see that easily. Now formal charge on oxygen number 1. Watch it. Oxygen number 1. Formal charge. Valence electron 6, we know, minus. How many are shared? 2 only. By 2. How many are unshared? 1, 2, 3, 4, 5, 6. 6. That makes it what? Minus 1. That makes it minus 1 on the whole. You got a minus 1. This also accordingly, minus 1. This should be 0. This should be 0. So you got this one as minus 1. This one also minus 1. Oh, you are getting it or not? What about this one? Valence electron 6 minus shared 1, 2, 3, 4. 4 divided by 2 minus unshared 1, 2, 3, 4. 4. That makes it 2. 6 minus 6 will be 0. This also should be 0. So you can see that, children, in SO4 2 minus molecule, sulfur is having formal charge of 0, 2 oxygens of minus 1 and 2 oxygen is 0 respectively in SO4 2 minus molecule. And this is helpful also when we are calculating bond order, because when I discuss molecular orbital theory, there I will take diagrams into consideration, and from there we will be in a position to find out the formal charge of different atoms respectively. Am I clear with thought here, children? Right. Now, if we want to find out general molecule, we have NH3. We want to find out the formal charge of nitrogen. Apparently, you can see that nitrogen has how many valence electrons? 5. So I'll write that 5 minus. How many are shared? Naturally, out of 5, how many are shared? Because there are 3 monovalent atoms. So how many will be shared? 3. So total number of electrons shared will be 1, 2, 3. From nitrogen 3, 4, 5, 6. So 6 by 2. Now, 6 by 2. Correct or not? Now, how many are there? Total 5. Out of which how many are shared by nitrogen? 3. How many are unshared? Naturally 2. So that makes it 2, 3, 6. 5 minus 5 will be 0. So nitrogen does not have any charge here in ammonia ion at all, NH3. But when you look on other molecule, which I showed a while earlier, which one? NH4 if you see. There will be no charge mentioned. You will be asked to find the formal charge of nitrogen. Clear or not? Right. Let us write down. What's the number of valence electrons? 5. How many are shared? 8. Divided by 2. How many are unshared? That will be 4. Unshared electrons will be how many there? No unshared electron at all. Clear. So that will make it 5 minus 4. That will be plus 1. Want to see how that is there? A while earlier I showed. Nitrogen, hydrogen and hydrogen. It had a lone pair of electron, and that lone pair of electron has been donated to proton respectively. Clear? So ammonia, NH3 is converted to ammonium ion. That's why we say NH3 is a Lewis base, because it's able to donate electrons. Did you get it clear, children? So when you take different molecules into consideration for the calculation of formal charges, you need to see the actual structure of that molecule as well. Let us see one example here. Say we have O3, ozone. What are the Lewis structures of ozone? 1 central atom oxygen. Correct, children? Or correct or not? Then you got, diagrammatic wise, I am not drawing it shape and geometry wise according to hybridization. I am just clearing the Lewis structures respectively. How many valence electrons it has? 1, 2, 3, 4, 5, 6. This oxygen also will have how many? 1, 2, 3, 4, 5, 6. This oxygen will have how many? 1, 2, 3, 4, 5, 6. Clear or not? General. Now, 2 bonds we will consider. It has made 1 bond with oxygen, and it has also made 1 bond with oxygen. Both of these have made 1 bond with oxygen. Clear? Now, how many electrons are remaining on this oxygen? 4. Is the thought clear here? Now, how many are there here? 1, 2, 3, 4. And it has made 1 bond 5. So 1 is still there free. So I'll make 1 double bond with it. Now you can see 1, 2, 3, 4, 5, 6. So this oxygen has made use of all the 6 electrons. Here 1, 2. Understand it. 1, 2, 3, 4, 5, 6, 7. That will be wrong. Correct or not? So total how many electrons are there on the whole? 6. So let us remove these off. 1, 2, 3, 4. If you give 1 electron here, there will be 1 unpaired electron oxygen. So according to structure, what happens is it is making a coordinate bond with one of the oxygens. So this oxygen is not using any of its electron for bond formation at all. Rather, it is just taking a lone pair of electron from the central oxygen atom and making a bond with other oxygen respectively. So have a look on this oxygen now. 1, 2, 3, 4, 5, 6, 7, 8. This is coordinate bond or not? Yes, because if you look in the bond lengths also, you will find out the difference according to NMR. But due to resonance, both of these bond lengths are same. Because this double bond can come here also, right or not? That's why children in O3, bond order is not 1. It is also not 2. Bond order is 1.5. Because this double bond does not precisely belong to these two. I'll mention this 1, 2 and 3. This double bond is not present here only. Why? Because there's a lone pair of electron. Correct, children? Right. So lone pair of electron at alternate positions, we have a double bond also. Right. So resonance can come into play when you have got pi electrons at alternate positions, or you have a negative charge and pi bond at alternate positions, or you have a lone pair of electron and pi bond at alternate position. Resonance is possible, correct? So due to that resonance, this double bond can shift around. So total number of bonds are 3 and total resonating structures for this will be 2. And what will be that? Oxygen, here double bond oxygen, now coordinate bond to oxygen. Now this double bond is between 1 and 2 here, and here it is between 1 and 3. Thus, when you are not able to show a single structure explaining all the properties of a molecule, resonance comes into play. We'll have a discussion on the concept of resonance in a broad spectrum respectively as well. So bond order, number of, if you want to find out bond order for polyatomic molecule, I'm going to do that in molecular orbital theory also. Here I'll tell you. Number of bonds, how many on the whole in both structures? 3. Bond order equals to polyatomic molecule. For a polyatomic molecule with more than 2 atoms, if you want to find out bond order, usually for a diatomic molecule, bond order equals to number of electrons in bonding minus number of electrons in anti-bonding divided by 2. But for a polyatomic molecule where you are not able to get MOT applied properly, because calculations become difficult and orbital overlapping becomes difficult. What does happen? Orbital overlapping calculation becomes difficult to be precise. Bond order for polyatomic molecule can be calculated by what? Number of bonds divided by number of resonating structures. So how many bonds are there in both the structures? There are 3. So there is 3 divided by 2, because total number of resonating structures are 2. 3 by 2 is equal to 1.5. Clear or not? Now you see, now if it is 1.5, it means that both the oxygens according to resonance are not stabilized, but they can be. Because when I calculate, this oxygen will have the formal charge of -1. Because this is -1 and there is no interaction between this and this oxygen has to be +1 and naturally this will be 0. Let us see whether I am correct in saying this or not. Right, children. So let us see for oxygen number 1. I will mention it here. So formal charge of first oxygen. What's the number of valence electrons? 6 minus. How many are shared? 1, 2, 3, 4, 5, 6. 6 by 2. How many are unshared there? 2. Clear or not? Oh, clear or not? So what does it become? 6 minus. It will be 3 minus 2. So that will be +1 or not? That's the apparent charge. That is the formal charge of this oxygen. Which oxygen? Middle oxygen. Why? What bond has been made here, children? Coordinate bond. Because it is coordinate bond, the electrons of central oxygen has been used. And once electron has been donated out, the number of protons in the central oxygen will exceed. Because how many electrons on the whole are there? 8. On the whole, 8. How many protons? 8. But 1 electron has been donated out to other oxygen for making coordinate bond. So how many protons are still existing? 8. And how many electrons will be around it now? Only 7. So what will happen by that? A positive charge will get expressed. That's a formal charge of this oxygen. Because this has lost out 1 electron and it is almost equal to gaining by the other. It's not ionic bond. Keep it in mind. It's almost equal to the gain by other because it's not making use of any of its valence electrons. That's what will happen. The charge on that oxygen will be what? -1. We can calculate that also. So what about formal charge of oxygen number 3? Faster. Valence electron 6 minus shared. How many? Only 2. Divided by 2. How many are unshared? 6. 1, 2, 3, 4, 5, 6. So 6 minus 1 minus 6, that will be minus 7. 6, 6 minus 7, that will be minus 1. You got minus 1 here or not? What is this one? Plus 1. This is minus 1. On the whole, when you show ozone, what do you show? O3. Do you show any charge? No. So on the whole, it is neutral. Plus minus, neutralize it. What should be charged on this oxygen? Naturally 0. Everything needs not to be done. It's a basic intuition in a concept which you can use for calculating it. Clear? Now, this oxygen, let us see oxygen number 2. Formal charge on oxygen number 2. Valence electron 6, shared. 1, 2, 3, 4. 4 by 2 minus unshared electrons 1, 2, 3, 4. 4. So that makes it 2 2s are 4. Minus 2 minus 4 minus 6. That will be 0. So this oxygen is 0. You got it clear, children? So this is how formal charge calculation needs to be done. So any molecule which will be given to you, it will not be mentioned of the charge. Charge will not be mentioned here. Is it clear? There will be no mentioning of charge at all. And you will be asked to find out in the given molecule how to find out the charge respectively. There are two ways of doing it. One, a good way is if you are able to draw Lewis structures properly. If you are not able to do that very properly, then this is the best way to solve the question very quickly. Did you get the formal charge calculation? The charge existing on the atom after everything has been removed from it. Means whatever is there is belonging to that particular atom only respectively. Is it clear? So formal charge can be calculated as Fc equals to V minus shared by 2 minus unshared electrons. Clear or not? So we have 2 more classes left for chemical bonding. One will be the concept of molecular orbital theory, and in that molecular orbital theory we will move into the resonating structures as well of different structures so that we can find out bond orders. Clear or not, children? So we are starting that discussion very soon, and at the end we will have a discussion of the full-fledged paper, competitive paper, for almost 2 hours, and I'll be solving different multiple choice questions there also. And keep it in mind, during my discussions only, I'm not taking any general theoretical consideration into order. These are all practical applications of the concepts which you need to make use of. If you are done with all the things what I'm discussing very cleanly here on the board, and very cleanly if you are keenly observing the things well, so everything is being done in the application manner only. So there is no theoretical consideration and there is no theoretical background I am developing for it, because basic fundamental application theoretical concepts I am giving. Clear or not, children? Yes. Read hard and keep reading. We'll see you soon. So we'll see you in my next class. Thank you. Have a good day.